Welcome to our discussion on linear regression. We're going to figure out how to calculate and interpret the correlation between two variables. We're also going to calculate and appropriately use a linear regression line for a given set of data to be able to predict other responses. So the last bit of data analysis we're going to look at in kind of basic statistics is evaluating the relationship between two variables. For instance, we could compare the heights and weights of people. And just as before, let's start by visualizing the data by putting them into some sort of table or graph and those kinds of things. Well, when we're dealing with what's called bivariate data, bi meaning two, like bicycles, variate, right, two variables. Bivariate data is when things have some sort of relationship between them. Basically, when an object is measured twice, that's bivariate data. So in the previous example, each teenage boy was measured for height and weight, right? Or you could have, each car is measured for price and miles per gallon. Those kinds of things. Then that's bivariate data. And we display bivariate data in scatter plots. I'm sure you've seen them before. It's just a graphical display of where those relationships land, because the x-axis will be one measurement. So for the teenage boy example, the x-axis could be, let's say, height, and the y-axis would be weight. And then a dot would represent the height and weight of one specimen, one boy, and then another dot, another dot, another dot. And if you were doing cars, the x-axis could be miles per gallon, and the y-axis could be price, and each individual dot would represent each car that you took that data from. A positive correlation between your variables just means as the x variable increases, so does the y variable. So for instance, with the teenage boys, as their heights get bigger, we would expect their weights to also get bigger. With the car, as the miles per gallon goes up, we would maybe expect the price to go up, right? If you get better gas mileage, they're going to charge you more, that kind of thing. A negative correlation means it goes in the opposite direction. As the x value gets bigger, the y value gets smaller. So maybe as miles per gallon goes up, price goes down because people don't want fuel-efficient cars, that kind of thing. That would be a negative correlation. So let's consider the relationship between the following variables and try and figure out whether it be positive or negative. So for instance, the number of cigarettes smoked, let's say, weekly or daily, whatever, and the probability of lung cancer. Well, wouldn't you expect that as the number of cigarette smokes goes up, right, as you smoke more and more and more, the probability of getting lung cancer should also go up, because we've shown scientifically, right, in multiple studies, that smoking causes cancer. There is a strong link between the two. So the more you smoke, the more likely you are to get cancer. So that should be a positive one. How about the number of minutes spent on social media sites by college students and their first semester grades? Well, wouldn't you think that if you spent more and more time just sitting around on Facebook and Twitter and Instagram and TikTok and all those kinds of things, you'd have less time for studying, and therefore your grades would go down. So this should have a negative correlation. If it has a correlation at all, right? It could be that they're not really that strongly related. How about the amount of credit card debt incurred by college freshmen and their IQ score? Well, there doesn't seem to be any logical reason why those two things would be related. So we would probably see just a big old buckshot scatter plot, and there wouldn't be any positive or negative correlation, because there shouldn't be any real correlation between those two at all. Okay, skill check. See if you can identify two variables that would likely have a positive correlation. Obviously, answers will vary, so just think of two things that would have a positive correlation. And while you're at it, see if you can think of two things that would have a negative correlation. Okay. The Pearson correlation coefficient, which is represented by the lowercase r, some books and some sources represent it by an uppercase r. So anytime you see the letter r all by itself, just know that it's most likely talking about the Pearson correlation coefficient. Round to the nearest thousand? Yeah, usually, not always, but it definitely is always a value between -1 and 1. It can't be anything else. A -1 means that you have a perfect one-to-one, perfect correlation between two things, and it's a negative, meaning as one thing goes up, the other thing goes down, and it's a perfect linear model. And a 1 means the exact same thing. You have a perfect linear correlation between two things, but in a positive direction, whereas one thing goes up, the other thing also goes up. You would never see that with real-world data. Those are just theoretical, right? I mean, we could set it up a set of data that works that way, but it's not going to happen by chance in the real world. If there's a strong correlation, then the numbers are just going to get closer to those extremes, right? You're going to get a number closer to -1 or a number closer to 1. And then as those numbers get closer to 0 on either side, right, whether it's positive or negative, but if it's close to 0, then that just means you're getting a weaker and weaker correlation, i.e. there's less correlation between those two variables. On the following page, we're going to see a small sample of data collected from male participants in a 161-kilometer trail ultramarathon. So the survey collected their body mass index, called BMI, and each participant their age. The table of data along with a scatter plot of the data is given, and we can use our calculators or some other technology to determine the correlation coefficient R between these two variables and then see if there's some sort of relationship between the two. Well, right off the bat with just the scatter plot, do you think there's a strong correlation between BMI and age? And hopefully you're looking at this and saying, no, I don't see any pattern, right? If there's a strong correlation, the dots should all line up in a nice pattern, and there is no pattern to this. There really isn't even an upward trend or a downward trend. They just kind of are straight, flat across, and not much of a pattern at all. So when we run this data, it's going to be a pretty terrible result, right? It's not going to really have a strong correlation. Okay, well, to run this data, you would hit the stat button and then edit, and you would enter your values into your two lists, list 1 and list 2. Normally, list 1 is going to be what you would consider the independent variable, and list 2 would be the dependent variable, or what's often called the predictor and response variable. So the predictor variable is the variable that you use to predict what happens in the response variable. The response variable is the thing that is somehow affected by the predictor. So here we would, between the two, if there was a relationship between the two, would you say that your body mass index would influence your age, or your age would influence your body mass index? I think you would all hopefully understand that obviously if there was a relationship, age would be the input, right, the predictor, and BMI would be the response. Because age is the only thing that we have control over, right? We can change our age by just simply aging, right? And then that might have an effect on our BMI. If we change our BMI, i.e. we diet and exercise and we change our BMI, there's no way that can change our age, right? You can't change your age. It just happens, right? So it makes more sense that that would be the independent and the BMI would be the output, right? So you can think of it input, output, right? X and Y. So the input should be in list 1, the output should be in list 2. So they told you to put the BMIs in list 1 and the age in list 2. They're just doing it in order. But I think it's always better to always put it in the order in which you think the model would work. Once you have them in both lists, then you go back to your stat menu, you tab over to the calculation menu, you page down to option 4, which is linear regression, you hit enter. You hit enter twice depending on what kind of calculator you have. There might be some other options that you have to tick on, but basically you need to tell it to run linear regression on list 1 and list 2. Then when you do that, you should get this output. If you don't get the R values, that means you have to turn the diagnostics on. Sometimes by default, the diagnostics are off. So for instance, with our calculator, you can see because I've got the fancier TI-84 Plus, when I run it, instead of just hitting enter twice, I need to tell it which list has my X values, which list has my Y values. Now it defaults to 1 and 2. So if you just put X in list 1 and list 2, then yes, you can just hit enter a couple times down and get down to calculate. But I put mine in list 3 and 4, so I had to change that, right? So I got to go down here and calculate it and run it. And you see how I don't have any R's. It gave me the A and it gave me the B, right? So I know what my regression equation is, but I don't have any R or R squared. That means my diagnostics aren't on, so I have to turn them on. To do that, you have to bring up your catalog. So second 0 brings up your catalog, and then you can see there's a little A here, meaning that it's waiting for a letter input, right? So you've got all these little blue letters. I'm sorry, all the little green letters, and we want to go to diagnostics. So if we click this, it'll basically page us down to the beginning of the D's. And then we just have to keep paging down till you see diagnostics off, diagnostics on, hit enter, and it puts it on the screen, and then you hit enter again, and it says done, meaning it's turned diagnostics on. Now if we go back to our stat, go over to calculate, go down to linear regression, it's still on, I'll move it down so you can see it, it's still on 3 and 4. And now if we calculate it, now we get R and R squared. Okay, so if you're using a TI and you don't get R and R squared, your diagnostics are off. Just go into your catalog and turn them on. And then you have everything you need. And you can see that everything matches, right? We're all good. Okay, now, because our R is 0.57, that's pretty weak, right? That's not great. It really needs to be up in the 8s or better to be considered strong. And it really depends on the size of our sample. This is a pretty small sample, so we should have a pretty strong one in order for it to be considered a pretty large one for us to consider it strong. And if you have a really large sample, you can have a weaker R and still consider that to be a strong result. It just depends. There's a relationship between the size of your sample and your R value. Level of confidence and level of significance. So the level of confidence C is the probability that the assertions made about the data are correct, and the level of significance alpha is the probability that the assertions made about the data are incorrect. So we always talk about alpha as being our error rate, right? And we normally set alpha to be 5%. So if we want to allow for a 5% chance of being wrong, then that means our confidence level is 95% because they have to add to 1, right? So if we have 5% error, that means we're 95% confident in something. Now, the critical values for the Pearson correlation coefficient, these are basically how big your R value needs to be. And in fact, it's how big the absolute value of your R has to be. Because if you have a negative R, right, it seems like that doesn't work. You just have to take the absolute value of it. So this looks for how big that absolute value of your R has to be in order to be considered significant at these levels, right? So if we let alpha be 5, 0.05, that's 5%. And that means this is at the significance level of we're 95% confident that this thing is accurate. If we set A to be 0.01, then we're now 99% confident this thing has to be accurate. It is just a coincidence that these two numbers are basically 1 minus alpha. Okay, N is your sample size. So in our previous example, right, we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 pairs of data. So our sample size is 12. If we go to 12, it says here that if we want to be 95% confident, right, have an error rate of only 5%, our significance level needs to be above 0.576. Well, in fact, it was 0.5763. It was just barely above it. So it's just barely considered statistically significant at the 5%. It's definitely not at the 1%. So if that, like I said, that absolute value of your R is greater than the critical value listed in the table, then we can say there's a statistical significance, which means it's unlikely that the relationship between these two variables just happened by chance. What it means is the relationship that we're seeing between these two variables likely actually exists. You'll notice that we never use words like it does. We're never absolute about everything. It's always we're somewhat confident about things, right? Statistics is all educated guesses. You can never be absolutely sure unless you have parameters, right? Unless you have a population of data, then you know exactly what's happening because you have all of your data. Since you almost never have that, you only have samples, we're just making educated guesses. So the wording of your solutions, right, when you're talking about what you got, it should always be a little softer, right? You can't be absolute. You can't say it is this, right? I'm sure it's this. It's likely this. I'm pretty confident it's this. It's those kinds of words. Okay, another example, right, where we're looking at, continue with that example where we're looking at our pieces of data. We can see that it's just barely significant because there are 12 values. But I mean, it's just barely significant, right? So yes, it's significant, but we have enough evidence to conclude that a linear relationship exists between BMI and age for these male ultra marathoners. But when you look at the scatter plot, that really tells me that sure, it's statistically significant, but what about the real world significance? What about the real world practicality of it? And graphically, there sure doesn't seem to be a good, strong relationship between those two things. And that's the problem with statistics is if you get a large enough sample, anything can be statistically significant. Now you might say to yourself, well, 12 isn't a very large sample. No, it's not. But it was large enough to make this stuff barely significant, right? So that's where you can get kind of misleading results. And if you don't really understand how to interpret things correctly, that's where you can think you get stronger results than what you really have. Okay, the regression line, also known as the line of best fit, is a straight line. Well, it's a straight line when we're doing linear regression. You could also do quadratic regression and exponential regression and polynomial regression where you try and fit curved lines to your data. But for us, we're doing linear regression, so it's a straight line that we try and fit to our data points. Now, it doesn't mean that we try and find a line that's going to go, where did I lost it? Where the heck is it? Sorry. There it is. I was one off. It's not that we're trying to find a line that goes through the most number of points. It's we draw a straight line such that the vertical distance from each dot to the line, the sum of all of those is minimized, right? So yes, you would like it to touch as many dots as possible, but touching a bunch of dots might not minimize, because if you touched a bunch of dots, it might make one distance really super huge. Whereas if you tilted the line up a little bit and made that distance smaller, all the other distances that would increase wouldn't increase more than the difference you would gain. You know what I'm saying? So you're trying to minimize all those vertical distances. Those are your error, because if you draw a straight line, let me just draw a straight line so you can see what the heck I'm talking about. So let's say we're trying to predict these things, and the line we get looks like this. Okay, goes right through this point. But you can see right here, we have this vertical distance. That means if we use the line to predict, right? So we come down here and we put an x value of 22.7, let's say. We put 22.7 into the regression line. It's going to come out and give us an answer of like an age of 39. But according to our data set, we had somebody with a BMI of 22.8 and their age was actually 29. So that's an error of 10 years, right? This one over here, the difference between the dot and where the line is the difference between 30 and 39, let's say. That's another error of 9 years. And you would add up all of these errors, and by moving the line, by maybe drawing it this way, maybe there's less cumulative errors. That's what they call it, the line of best fit. It best fits your data. It minimizes those vertical distances between the prediction you would get from the line and the actual value you have in your data set. Just like any other straight line, right? A is your slope and B is your intercept. And of course, if we were doing other types of regression like exponential and things like that, you would have an equation for an exponential equation or a polynomial or a quadratic and things like that rather than just a straight line. So here's another example. A recent study sought to find if any correlation exists between childhood weight and self-esteem. Children between the ages of 9 and 11 were surveyed. Weight was measured in pounds. Self-esteem was measured based on the average of the answers to 15 questions, asking the participants to rate themselves on a good old Likert scale of 1 to 5, where higher scores mean higher self-esteem. Here's the data for the 12 cases. So their weight and their scores. Remember, a higher score meant higher self-esteem. So a higher number would mean they feel better about themselves. If we put this data into two lists in our calculators and run it, we can then answer these questions. So to figure out if it's statistically significant, we first have to calculate R. We put everything in our list, we calculate it, and if you guys want to pause the video and put this into two lists and try it, I recommend you do that. Just make sure you understand how to do the process. You should get an R of negative 0.6051. And then to figure out if it's significant or not, we got to go back to our table, right? Well, how many pieces of data do we have? 2, 4, 6, 8, 10. We're at 12 again. Well, according to our data, the absolute value of R needs to be 0.576 or better. Ours is 0.651, so we're significant at the 5% level, an alpha of 5, but we're not significant at an alpha of 0.01. So the question was, is it significant at 0.05? Yes. Is it significant at 0.01? No. Okay, so you can see that it depends on how accurate you want to be. 0.05 means we're 95% sure that it's significant. 0.01 means we're 99% sure that it's significant, and in this case, it is not. So that's how the differences work. Okay, that doesn't mean we're 99% sure it's not significant, because remember, we were already 95% sure it was significant. We just can't say that we're 99% sure that it is significant because it fails at that level, right? So it doesn't turn around and then say that we're 99% sure that it's not significant. Just know that doesn't work that way. Again, if we ran the data, we would get these values. So part B, when it asks for the linear regression line in the form of AX plus B, which is the same thing as MX plus B, right? We're just using A instead of M. Then there's our A, there's our B. We put it all together, and we get this. Which means, remember, what was X? X was the weights, and the self-esteem scores was the Y's. We're trying to guess how good they feel about themselves based on their weight. So when we have this equation, that means their BMI would be 8.72 when X was 0, meaning when their weight was 0, if they didn't weigh anything, they would be really, really happy about themselves, right? So obviously this thing doesn't work for all values of X because you can't have a weight of 0. Heck, you couldn't even have a weight of 10 or 20 because then you'd be a baby, and a baby doesn't have any self-esteem. It's not really self-aware at that point. Okay, but anyhow, there's our prediction equation. So part C, if appropriate, predict the value of the level of self-esteem given that the child weighs 64.1. Well, we already showed that it's significant at the 0.05 level. So it's appropriate for us to use this equation to estimate. If we wanted to do it at the 0.01 level, we couldn't use it. So at this point, we can put 64.1 into the equation, which is our X. Multiply it by this, add that to it, and we get 3.337. So basically, if the child weighs 64.1 pounds, they're going to have a self-esteem score of around 3.3. That's what that means. That's all that means. Okay, if appropriate, predict the value for the level of self-esteem given to a child that weighs 45 pounds. If we look at our table of values, we don't have anybody that weighs 45 or below. The smallest value is 54.3, and the largest is 88.1. You can technically really only predict in between your minimum and your maximum. You don't want to try and predict outside of your variables. Now, if you have a really strong predictor, if your equation had a much better R, then you can predict outside your range. But because of this, it's really not appropriate to predict outside of our range. Now, last one, if appropriate, predict the value level of self-esteem given that 13-year-old weighs 88 pounds. Again, it's not appropriate because it falls outside of our range, right? 88.1 is the top end of our range, so it's pretty close to the outside. If appropriate, predict the value of the level of self-esteem given that the 13-year-old, the reason why this is a problem is it's a 13-year-old, and the data came from 9 to 11s. So they're the wrong age, right? Because obviously the older you are, the more you're going to weigh, usually because you've grown, so the whole thing is going to be thrown off. All right, that's all I got for you.